Recall that for a beam for which is continuously laterally supported on the compression side, and made of a compact section, the nominal moment capacity is given by the yield stress times the plastic section modulus about the axis of bending. And the load factor, the resistance factor for bending is 0.9, and so the design strength is phi times mn, and the phi equals 0.9 for bending. Now this information is cataloged in some convenient tables in the AISC manual for certain sections, including W shapes for material strength 50 ksi. So the sections are arranged in decreasing order of strength, or decreasing order of the plastic section modulus, which also means decreasing order of strength. So decreasing order of plastic sectional modulus and decreasing order of strength. And they're also grouped together in such a way that the topmost section in the group is the lightest section. So essentially they're ordered in decreasing order of strength and then grouped in such a way that within the group it's increasing order of weight per unit length. So let's look at an example of how to use these tables to select a W shape. So let us consider a simply supported beam of span 25 feet. Continuously laterally supported. And the dead load consists of a uniformly distributed load of 1 kip per foot. So the dead load is 1 kip per foot. And the live load is simply a point load of 35 kips at midspan. This is the live load. And let's say that we want to use A992 grade 50 steel. So the yield stress is 50 ksi. And we want to pick the lightest, select the lightest W shape that has sufficient strength. So let's calculate the bending moments first. So we calculate the bending moment due to dead load is 25 kips per foot times, 1 kip per foot times 25 feet squared divided by 8. It's WL squared over 8. That's equal to 78 kip feet. The bending moment due to live load is 35 kips times 25 feet divided by 4. PL over 4. That works out to be 219 kip feet. Let's also calculate the shear forces. We'll see in a little bit why. So the maximum shear force due to dead load is 1 kip per foot times 25 feet divided by 2. That's 12.5 kips. And the shear force due to live load is simply 35 kips divided by 2. So that's 17.5 kips. Now let's apply the AISCM load combinations. So we do 1.4 times dead load. That turns out to be 109 kip feet. And then 1.2 times moment due to dead load plus 1.6 times moment due to live load. That works out to be 444 kip feet. And clearly this controls. Let's do the same thing for shear force. 1.4 times shear force due to dead load is 17.5 kips. 1.2 times shear force due to dead load plus 1.6 times shear force due to live load works out to be 43 kips. And this controls. Now let's go to the AISC table and try to see if we can find a W shape. So we go to the tables and start looking for a moment capacity of 444 kip feet. So we see that these moment capacities are very large. We keep scrolling down. It's starting to get to the range we're interested in. And we come over here and we notice that a W12 by 79 has a moment capacity of 446 kip feet, which is more than the 444 we need. But we might as well pick W21 by 55, which has a capacity of 473 kip feet, because this is actually a lighter section than the W12 by 79. Now, there may be other restrictions like headroom. W21 is a deeper section, so it being the lightest section may not be the only consideration. Maybe we're looking for headroom and we need a W12 or a W14. So other considerations may drive the selection of other sections, but if we're only interested in the lightest section, then we can pick the W21 by 55. Another thing we'll see later is we'll check deflections. So if we pick the W12 by 79, it may be okay in terms of strength, but it may not be okay in terms of stiffness that we need for deflection. So these are the various considerations as we pick a section. But in this case, we need 444 kip feet. Anybody higher than this in this group will do, and we pick the W21 by 55 based on it being the lightest section. Now, having picked that section, we check the shear strength. We need a shear capacity of 43 kips. We have 234 kips. So shear is not controlling here. And that's generally the case for standard W sections, that it will be bending that controls and not shear. Shear may have some significance when doing built-up sections and plate girders. But in most cases with standard W sections, moment will control, as we see here. So we can say use W21 by 55, whose phi mn, moment capacity, is 473 kip feet, which is greater than the 444 kip feet. So we're okay. And shear is okay too. Now let's check deflections. This is related to serviceability. And notice that, recall that deflections have to be checked with service load, the unfactored loads. So deflection at midspan. Based on service loads. The dead load is a uniform load, so we have 5WL to the power of 4 divided by 384 VI. These are things you can look up in any structural analysis reference. Plus, we have the 35 kip live load, which is a concentrated load, PL cubed over 48 VI. And we are using the unfactored loads because we use unfactored loads for deflection. So this is going to be 5 times one kip per foot times 25 feet to the power of 4 divided by 384 times E is 29,000 KSI, which we have to convert to per square foot, so 144 square inches per square foot. And we need to look up I, so we go again to the AISC tables and identify W21 by 55, and we see that its IXX is 1140 inches to the power of 4. So it's 1140 inches to the power of 4 divided by 12 to the power of 4 inches to the power of 4 over feet to the power of 4 plus 35 kips times 25 feet cubed divided by 48. E is the same as above and I is the same as above. And if we do this calculation, we get 0.6 inches. Now, usually this 0.6 needs to be under some acceptable limit that is determined by acceptable deflection and floor vibration criteria. So the smaller the deflection due to the load, the stiffer the floor is and less the floor vibration issues are. So all this is usually specified in terms of a deflection that's in terms of a certain fraction of the span. So for example, L over 240 is a typically used fraction of the span, which works out to be 125 inches. So 1.25 inches. So this is less than L over 240. So, okay. If it happens that the deflection exceeds the limit, then we may have to go and pick a bigger section over here. And in that case, the section will be controlled by deflection and not by strength. So this is an example of how to use the AISC tables to pick an adequate W section for the design of beams.